Hello everyone, my name is Ming Chuan from Group 3F and today I'll be presenting Integrated Project for Reaction Engineering part. So first of all, we have types of reaction involved. Basically, the steam methane reforming process consists of two main steps. They are the SMR reaction denoted by R1 and water gas shift reaction denoted by R2. So basically, the SMR reaction is from methane with excess of H2O producing CO plus 3H2. The next step is the water gas shift reaction R2. R2 consists of CO from the first reaction, as you can see, CO, and with excess of steam producing CO2 and H2. So here we have a block diagram. The natural gas comes in to the first reactor, the SMR reactor, and then the product goes to the second reactor, WGS reactor. So these two are take-back reactors arranged in series with hundreds of PFR tubes filled with catalyst. For the catalyst part, we have nickel alpha Al2O3 for the first reaction. These three are the reasons why we choose nickel alpha Al2O3 as the catalyst for reaction 1. As for reaction 2, the catalyst is MgFe2O4. And that is all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Najah binti Sahimar, 2.2 kinetic data. We can see for SMR or reaction 1, we have two ways to find the reaction order. First, we use the article. Second one, we are going to prove the statement from the article by using integral method. So from the article, the first one is from the Hughes and Hughes. Rate of reaction is first order. So same goes to second article done by Dix, Poynton and Cedar. They also state that the reaction order is always close to 1. So here we are going to prove by calculating the reaction order by using integral method. We are going to plot the graph of X versus W over F. Next, when the rate order is equal to 0, we got this not too linear graph. Next is when rate of order equal to 1. So we can see that the graph is quite a linear graph with the K value is 0.0199. And next is when rate order equal to 2, we can see that the graph is not a linear graph. So based on the plots above, it can be observed that the best fit linear graph is when alpha equal to 1. So here by using integral method, we prove that the rate of order is equal to 1 based on the both article that we found. Okay, next we are going to find the activation energy for SMR. By plug in all the values in the Arrhenius equation, we can get this value for rate constant extended condition, 4.858 times 10 to the power of negative 36. By using Arrhenius equation that relate the rate constant to temperature, same, we are going to plug in all the value in this equation and we will get the final answer for activation energy. So for WGS, we didn't find any article that mention about the reaction order for the reaction in WGS. So we are going to prove it only by using integral method. Same step is used. We are going to plot for alpha equal to 0, alpha equal to 1 and alpha equal to 2. So the most linear graph that we get is alpha equal to 1. You can see in our final report. So for activation energy also the calculation is same with SMR.
Moving on to 2.3, we have strategies to maximize the selectivity and yield of H2. Before we proceed, we need to make some basic assumptions. Moving on, the selectivity of H2 can be observed through first, conversion, temperature, and the ratio of steam to methane. So based on this graph, as you can see, this means that in contrast, the selectivity of H2 is high at higher methane conversion. The next factor is temperature. H2 selectivity can be increased by lowering the operating temperature at water gas shift reaction. Next, the ratio of steam to methane. To minimize the reverse reaction, the S/M ratio should be decreased to further enhance the selectivity of the desired product H2. Next, we need to determine the strategies to maximize the yield of H2. The yield of H2 can be maximized through variation of temperature, pressure, and molar steam to carbon ratio. First, it is the effect of temperature. The yield of H2 can be observed to be increasing with increasing temperature. The next factor is the effect of pressure. So the conversion of both CH4 and H2O at fixed temperature goes down as the pressure of the system increases. The last factor is the ratio of steam to carbon. The proposed optimum S/C is 3 at constant temperature and pressure.
So hi, now I am going to present about this part, which is 2.4, the optimal operating conditions. So in this part, I'm going to focus more about our overall block flow diagram for our design. So as you can see, this is the 4 main unit that we use in our design, which is SMR or steam methane reformer, water gas shift, CO2 absorption unit, and pressure swing adsorption unit. So in the first two unit, we use it to enhance the production of H2, where we know that in both two unit it will produce hydrogen. So the first unit is supply the steam, and the steam will react with methane to produce carbon monoxide and hydrogen. So in water gas shift, it will also produce hydrogen by reacting carbon monoxide and also water. In water gas shift also it will produce carbon monoxide. So we need to have CO2 absorption in the third unit because we want to get rid of the CO2. So next step, we are going to find the amount of methane that we need to supply in order to have the desired H2 produced at the last unit, which is 30,000 ton per year. So we are going to follow these 5 steps, and the amount of methane required is 448.01 kmol per hour in order to produce 30,000 ton per year. And then for next part, which is isothermal reactor design, we construct stoichiometric table for both SMR and WGS in order to find the flow rate of each species in both reactor. For commercial reactor sizing, as it is a packed bed reactor, we are going to find the weight of catalyst used instead of the volume. So follow this calculation, and then we can find the weight of catalyst needed for SMR and also WGS.
Assalamualaikum and good morning. My name is Mubarak bin Muhammad Taufik, and I will be presenting the separation process 2 part. Designated production of hydrogen is 30,000 tons per year with purity of 99.99%. In separation process part, we are only focusing on hydrogen enrichment unit. So the PSA, pressure swing adsorption, is commonly used to separate gas mixture and thus applied in purification of the hydrogen gas. And for the multiple adsorbents that are used in each layer of the bed, the first layer, the common adsorbents are alumina or silica gel to remove water vapor. The second layer, activated carbon, and the third layer consists of 5A zeolite. The primary concern while choosing the type of adsorbent used is when concerning the largest molecular size to be absorbed versus the pore size of the adsorbent. As for example, zeolite should not be expected to provide any adsorption area for molecules larger than its pore, nor for molecules for which it does not even have affinity. The affinity of the adsorbent for some types of substance can be much greater than the affinity for others. Carbon, which is neither fully hydrophobic or hydrophilic, retains some adsorption area with affinity for both polar and non-polar molecules. As for zeolite, all naturally occurring zeolite is hydrophilic, having an affinity for polar substances such as water, but synthetic zeolite can either be hydrophilic or hydrophobic. Based on our findings, we have chosen to use the activated carbon added with 13X zeolite because of the design used for gas application, and it has rapid adsorption kinetic. 13X zeolite has been successfully used in PSA processes for air separation and also for helium purifications. So By comparing all the natural gases in activated charcoal and 13X zeolite, carbon dioxide turns out to have the highest affinity in both adsorbents. So, Langmuir-Freundlich isotherm includes the knowledge of adsorption heterogeneous surfaces. It describes the distribution of adsorption energy onto heterogeneous surface of the adsorbent. Langmuir-Freundlich isotherm consists of several parameters, and these parameters can be obtained by using the nonlinear regression techniques.
Now with the adsorbent of activated carbon plus 13X zeolite and the isotherm of Langmuir-Freundlich model, we're here to continue with hydrogen purification by PSA or pressure swing adsorption. In pressure swing adsorption, there are few sequences involved, which is shown here. For our project, we chose to use a 4-column PSA cycle. This is the figure of a 4-column PSA cycle with the sequences of each column. In analyzing the performance of 4-column PSA cycle, we found two clashing articles, which one said that a recovery can only acquire it with 72.68%. However, research from Delgado said that with the 55% composition of activated carbon, we can still acquire a productivity of 90.3% with a purity of 99.99%. Next, we go into upscale. To begin, we need a formula which is provided by Delgado et al. For hydrogen productivity. Next, from the article, we managed to acquire this data to be involved in our calculation. A few assumptions has been made for this calculation. The calculation starts with volume of activated carbons and zeolite. With the volume, we then calculate the mass using density. Then, using the dimension of the column given in the article, we calculate the production of H2 per year, but we then found out that it was not enough to achieve 30,000 per year, and a scale up is required. And we use the same properties as mentioned, except for these following exceptions. Next, we then calculate the new values for the new column. We first calculate the mass of the adsorbents in the new column, and then using the mass, we can use the formula to find the volume. From the volume of the new column, we then can find the dimension, which is the diameter and the length, using the given formula. And then, for mass transfer zone or HUNB, we gather the data from the articles to find TU and TT to find HUNB. Next, we go into mass balance. With the given 30,000 tons per year of hydrogen, we can calculate the mass balance with the help of data from the articles. After calculating, we can find the amount of CO in the inlet of H2, and then the total mass flow rate in and all the mass flow rate of each component. Finally, strategy to achieve 99.99% H2 purity is we use 4-column PSA cycle. We use a 3-meter diameter and a 30-meter length column with a mass transfer zone of 3 meter, where adsorption and desorption happens alternately in each column.
So for the reflection part, students are required to do integrated project based on knowledge from process modeling and simulation, reaction engineering 1 and separation process 2. So how do we feel? So at first we feel very lost. Then obviously we kind of feel annoyed with lecture, but we feel relieved and energized. And lastly, all of us feel very satisfied because the work can be done within the timeline that we had set. Then for the evaluation, we have to evaluate what was good and what was bad during the project. So now we have to analyze why was it good and why was it bad. So for the initial division of work, it was good. For the second part, the slow communication. And lastly, the bad thing is we are unsure about the requirements of the project. So the conclusion is, for a group project to be good, we need to plan ahead on how we want each section to look and feel like. We need to be more flexible to avoid unnecessary conflicts. We have improved communication skills. For the action plan, So first, we have to discover personal strengths and weaknesses before dividing any task. And second, we have to clarify on the format of the assignment. Next, we need to suggest everyone to follow the agreed milestone. Lastly, we have to voice out any opinions that might be helpful for the progress of the project.